Assalamualaikum sir, I am Shushmita Mitro. Now I will presenting my solution for the digital parking control system assignment. According to my ID number, the maximum capacity is 12 cars. In the first question, at first we need to draw the system architecture with the block diagram. Here the system uses entry and exit sensors to detect the vehicle movement. An up and down counter keeps the track of the number of cars in the garage. The register 1 stores the current count from the up and down counter. The keypad is used to initially set the maximum available space, which is then encoded and stored in a register. The register 2 stores the total parking capacity. Here the total capacity is 12. This value can be set using a keypad by an encoder, which is 4 into 16 encoder, and comparator is used here. It compares the current car amount from register 1, that is P, with the maximum capacity from the initial keypad input. Here it is A. In the comparator, there is a condition A is greater than B. It means the maximum capacity is greater than the current count. It triggers a 555 timer in a stable mode, as it is continuously produced on off cycle that perfectly suited for this purpose to blink the space available message on a 7 segment display. And when the condition is A equals to B, that means the maximum capacity is equal to the current car account. It then triggers a 555 timer in a monostable mode, as it generates a single output pulse of a specific that is to display full on a 7 segment display. In the next slide, the operational sequences are done through the flow diagram. At first, start system initializes, then maximum space set with the maximum capacity 12 cars in my case is input via the keypad. Initialize counter at 0. The system constantly checks the entry sensor. If a car is detected, it means yes, the counter increments. If no car is detected, it means no, it proceeds to check the exit sensor. Exit sensor checks if a car is detected, it means yes, the counter decrements. If no car is detected, means no, it loops back to check the entry sensor. Overall count counter maintains the real time number of cars in a garage. The comparator compares the current car count B with the maximum capacity A. If A equals to B, it means yes, the full display is activated. If A is not equal to B, the space available display is activated. The process then loops back to continuously monitor the sensors and update the display. Here, for counting cars, a 4-bit synchronous up-down counter is used, as it is sufficient for our 12 cars capacity. It details sequence of the counter operation from clock 0 to 15. The counter has an up input and down input, where when up is high, the counter increments. When down is high, the counter decrements. The logic for each flip-flop's J and K input is derived from the desired up-down sequences. For a synchronous up-down counter, these equations ensures the current next state based on the current state and the up-down controls. These equations, along with the common clock signal, allows the counter to accurately track the number of cars. The counter is built using 4 JK flip-flops FF0 to FF3, each representing 1 bit Q0, Q1, Q2, Q3. All flip-flops are driven by the same clock that makes it synchronous. The JK inputs of each flip-flops are connected based on logic conditions, which will control whether they toggle. Now let's discuss how I activate the full and space available displays using 555 timers. This display needs to blink, so I use the 555 timer in stable mode according to my ID number. Here P is 54 and the duty cycle is 46%. This means the display will be on for 46% of the cycle. Then the frequency is 10 Hz. That means that time period will be 0.1 second. After calculating, I found that the time of high pulse TH is 46 millisecond, and time of the low pulse TL is 54 millisecond. When I need to choose R1, R2 and C values to achieve this TH and TL times. Here I choose 250 microfarad, as if I choose 50 then the resistor value will be large. Again, if I choose 470 microfarad, the resistor value will be very small. So here I consider 250 microfarad, yeah, as it allows to use resistor values in a practical and standard range. Then calculating the values, I found that the value of R1 is 266.40 ohm and the value of R2 is 311.69 ohm. Here, for achieving the duty cycle of less than 50%, we use the formula R1 divided by R1 plus R2 into 100%. Then we modify the circuit by placing a diode in parallel with R2. This allows the capacitor to charge through R1 only and discharge through R2 only. This gives us better control over the duty cycle, especially for values below 50%. Here the system uses two 555 timer circuits, one in monostable mode and another one is in astable mode, controlled by a comparator to display parking status. When the comparator output equals to B, indicating the garage is full, it triggers the monostable 555 timer through pin number 2, causing its output to go high and activate the full display continuously. The reset pin is tied to VCC to prevent accidental resets, and timing components are connected to pin 6 and 7. When A is greater than B, indicating space is available, it triggers the stable 555 timer. In this mode, pin 6 and 7 are connected to resistor R1, R2 and capacitor C with a diode T1 across R2 to achieve a duty cycle below 50%. The output of this timer brings the space available display according to the calculated value of TH and TL times. This design ensures the correct message is shown, either steady or blinking, based on real-time parking condition. In the question number 3, we needed to design an FSM that outputs A for TH millisecond and then B for TL millisecond with a clock period of 1 ms. In the previous question, our calculated value for TH was 46 milliseconds, so the adjusted TH value will be 4 millisecond, and our calculated value for TL was 54 milliseconds, so the adjusted TL value will be 4 millisecond. The state diagram shows the sequence of state. We need to 4 states for A and 4 states for B. So a total of 8 states. This requires 3 flip-flops, means 2 to the power 3 equals to 8. States could be represented as 000 to 111. The FSM transitions through 4 states while outputting A and then transitions through 4 states while outputting B, and then repeats. A reset input is included to bring the FSM back to the initial state 000. The present state PS2, PS1, PS0 is the current state of the FSM. The rising edge is the clock. The state FSM, FSM will transition to a next edge. Next clock edge is NS1, NS2, NS1 and NS0. A and B is the corresponding outputs for each states. For the first 4 states, 000 to 011, output A is high and B is low. For the next 4 states, 100 to 111, output A is low and B is high. From the state table, we derive the simplified Boolean expressions for outputs A and B. Here A equals to PS2 bar. A is high when PS2 is 0. Again B equals to PS2. B is high when PS2 is 1. This simplification is based on the state assignment where the most significant bit PS2 determines whether A or B is active. So here in the Verilog HDL code, we see that there is a finite state machine module TLC binary that defines the module with inputs clock, reset and outputs A and B. It uses a 3-bit register P state to store the current state, which updates on the positive edge of the clock, and a 3-bit register N state to store the next state. Here the block describes sequential logic triggered on the rising edge of the clock. If the reset signal is high, the state is reset to 000. Otherwise, the P state updates to the end state on the clock edge. The end state is derived by simply incrementing P state, causing the FSM to cycle through all 8 possible 3-bit states. The code generates two outputs A and B, where logic is directly tied to the most significant bit of the current state, with A being high when that bit is 0 and B being high when it is 1. This Verilog code essentially implements the FSM logic to generate the required A and B output based on the timing requirements. Question number 4. First, we describe the limitations of block diagram and counter design. The limitations are fixed capacity sensor limited to 12 cards only due to 4-bit counter limit. Another limitation is sensor dependency. The system dependent on entry and exit sensors, so that sensor malfunction or noise can lead to inaccurate count. Lack of error detection. There is no way to detect or correct counter errors from missed or false sensor triggers. No memory, losses data if power is disconnected. The another limitations of the another part is the limitations of a 555 timer based display. Here the limitations are no enable control, no enable pin to control operation externally, and another is fixed blinking. Blink's rate is determined by fixed resistor and capacitor, so that it can't change dynamically. Now the modifications. Use higher bit counters. Integrate microcontroller for more flexible control logic. Add enable or reset input logic for 555 timers. Use multiplex displays to control many displays with fewer pins. The impact of scaling. More bits in counter increase flip-flop count. FSM becomes more complex. Timer and display control logic must support greater resolution and state handling. Need for power supply adjustment and logic gate expansion. So these modifications would transform the system into a more scalable and versatile solution. Thank you, sir. That's the summaries of my solution. Assalamualaikum, sir.